In this problem, we are given a storage box with a square base, and it should have a volume of 90 cubic centimeters. The top and bottom surfaces cost $0.60 per square centimeter, whereas the sides cost $0.30 per square centimeter. And in this situation, we have to determine the dimensions of the box so that the volume is minimized. So let's see how to determine that. Let x represents the side lengths of the square base and y represents the height of the box. So as we can see from the figure, the length of the box is x squares x centimeter, and the width of the box is x centimeter, and the height of the box is y centimeter. So in this situation, we have to determine the two equation, that is one for the constraint and the other one is the optimization equation. We create this constraint equation using the volume information, and we create the equation using the surface area of the box times the rate of the each of the surfaces. So first, let's create the constraint equation. So I'm going to write down the volume of the box. The volume of the box is length times width times height, and this is already given as 90 cubic centimeters. And so let's write down this as length is x, width is also x, and height of the box is y. And so this equals 90. Let's simplify this. X times x is x squared times y is x squared, y equals 90. So let's say this is equation 1, or this in fact is the constraint equation. Now let's see what is that we have to optimize. Since we have to determine the dimensions so that the cost is minimum, we identify that the optimization is the cost. We have to optimize the cost of making this box. So first, let's write down the cost equation. So we write cost, and this equals surface area of the box times the rates of each of the sides of the box. So first, I'm going to write down the surface area of the box. The surface area, we see that it has a top and bottom surfaces. This one is top, and at the bottom we have both are square bases. So we can say that the area of the top surface will be x squared, and the bottom surface will also be x squared. And as far as the sides is concerned, we have four sides: the front, the rear, the left, and the right. For each of the sides, the area of the sides will be length times height, that is x times y. Since we have four sides, we write down this as 4x squared. I'm sorry, it is 4xy. So therefore, we can write down the surface area as the top plus bottom, and then the four sides, which includes the front, the rear, the left, and the right. So the area of the top and bottom surfaces, we write down this as x squared, and since we have x squared represents the area of the base, and similarly we have the top which is also x squared. Adding them together, we get 2x squared, and then area of each of the sides is xy. Since we have four sides, we multiply this by 4. So this one represents the surface area. Now let's write the cost equation. So we write cost, let C represent the cost, and this equals surface area times rate. Uh, from the question, we understand that rate is given separately for top and bottom as well as for sides. So this one represents the area of the top and bottom, which means we have to multiply this area times its rate, which represents the top and bottom. For top and bottom, we have to consider $0.60 per square centimeter. So I write down the rate as 0.60. This has to be multiplied with the surface area of the top and bottom, plus we put the area of all the four sides, which is 4xy, times its rate, that is the rate of each of the sites cost $0.30 per square centimeter. So we multiplied this quantity by 0.30. And let's simplify this cost equation. We multiply the numbers 2 times 0.60, and this equals 1.2, and then we have x squared, plus we also multiply this 4 with the 0.30, and that also is 1.2. We then have xy. So this one is a constraint equation. But to optimize this cost, we need this equation in just one variable. We see here that we have the variable y. So we can convert that into x using the equation number 1. So let's use the equation number 1. So here I have this equation number 1, which is x squared y equals 90. Now let me solve for y from this equation. This one equals 90 over x squared. So we can plug this equation for y into here and make this cost equation in just one variable. So I'm going to write down this as a function notation because this will be converted into x. So we have 1.2 x squared plus 1.2 x times, replace y by 90 by x squared. And we can also simplify this. We see that we can cancel this x with this x squared as 1 times. So it's basically 90 by x. And so we write the cost function c of x. This equals 1.2 x squared plus 1.2 times 90 over x. Observe that we have 1.2 in both terms, so we can factor it out. Therefore, we write c of x, and this equals 1.2 times x squared plus 90 by x. Now to optimize this cost function, we should set up this equation and determine x from this one. Basically, we use the calculus method to determine the critical point of the cost function, which usually gives the minimum cost. So let's find the derivative of this cost functions. I'm going to differentiate both sides with respect to x, and c prime of x equal to 1.2 times the derivative of x squared is 2x using the power rule, and then here we have 90 by x. So it's basically we can consider this as 90 times x power minus 1. The derivative of x power minus 1 is minus 1 x raised to the power of minus 1, or otherwise we can write this as negative 90 divided by x squared. So this one is the derivative of 90 by x. I'm going to change this to negative 90 over x squared. So here we have obtained the derivative of the cost function. Now we have to equate this to 0 and find the critical point of this function. So this replace c prime of x by 0, and this gives 1.2 times 2x minus 90 by x squared. And so from this we can solve for x. So dividing both sides by 1.2, we will get only 2x minus 90 by x squared equals 0. Let's solve for x from this one. So I add 90 by x squared to both sides, which gives 2x equals 90 by x squared. Multiplying by x squared, we get 2x cube equals 90. And so we divide by 2, which gives 90 by 2. And this equals 45. So we take cube root on both sides, which gives x equal to cube root of 45. And this is approximately 3.56. So we have identified the critical point of the function is 3.56. Now we will verify whether at this critical point the cost is minimum. And for that, we should find the second derivative. So let's find the second derivative of the cost function. So let me copy the first derivative, that is c prime of x equals 1.2 times 2x minus 90 by x squared. Now let's find the second derivative, and this equals 1.2 times the derivative of 2x is 2 minus here we have to find the derivative of 1 over x squared, which we can consider as x power minus 2, and its derivative when we use the power rule we get negative 2x raised to the power of negative 3, or otherwise we write this as negative 2 divided by x cube. So let me copy it here, which is negative 2 divided by x cube. Let's simplify this. So we have second derivative of cos function. This equals 1.2 times. We have negative and negative, so they become positive. So it is 2 plus 90 times 2 is 180 divided by x cube. Now we have to use this critical point and plug it here. And when we do that, we can easily see that it is going to be positive. That is C double prime of 3.56. This equals 12 times of 2 plus 180 divided by replace x by 3.56. So it is 3.56 cube, and this quantity is greater than 0. We do not have to calculate the exact numerical value. This one is positive and this 2 is positive, and we are adding it with another positive number. So overall the cost function is going to be positive when we plug it x equal to 3.56, and this means according to the second derivative test the cost is minimum at this critical point, that is at x equals 3.56. So thus we have verified that the dimension x equal to 3.56, the cost is minimum, which means we can now find the height of the box, that is y, and for that we will use the equation 1, that is x squared y equals 90, or otherwise x squared y, this one is y. Solving for y from this, we get y equals 90 over x squared. So let's plug it into this equation. 90 over, replace x by 3.56, we get 90 over 3.56 squared. And when we plug this into the calculator, we get approximately 7.10. So therefore, we see that x equals 3.56 centimeter, and y, which represents the height of the box, equals 7.10 centimeter.